Today, we'll be going through a brief introduction about safety autonomous levels and what would be the driver and system overlap and the relevant safety measures or the complexity of the safety measures that is required at that levels, followed by the safety challenges, and followed by the overall fail operation systems evolution and what is becoming more complex, and then different redundancies, how do we consider them, what are the aspects of them, followed by commercial vehicle braking example case studies. Okay, so a little bit background about ZF CVS, former WAPCO, one of the leading supplier for commercial vehicle systems, integrated with ZF globally from 2020. Basically, we have complete range of products, right from components, air supply units, chambers, and pressure sensors or sensors to systems, complete systems like brake systems, ADAS systems, steering systems, to the aftermarket solutions like solar panel solutions or blind spot detection solutions, or then followed by the digital market solutions like vehicle location tracking devices or aftermarket service support and all. And for all the trucks, buses, trailers, and tractors. And some of the basic systems are more like drivelines, that is components, driveline components, then e-mobility, transmission systems, and gearboxes, and brakes, steerings, and off-highway, that is 25119 perspective, agricultural vehicles, and so on. And looking from the vehicle perspective, these are the solutions that we provide. That's almost complete range of the vehicle chassis systems. Okay. Now coming to the level of driving automation, the first level, that is standard driver control, full driver control, no system, no autonomous system in place. So full responsibility with the driver to ensure the longitudinal and lateral control. And next level, the driver will control, but supported by the system at lateral or longitudinal with a limited one. So if you see the eyes off permission, the driver is not supposed to take the eyes off from the system. So he should be attentive continuously. Okay. And then what should we take care? Primarily that the systems, so the primary scope from the safety side would be more of monitoring the sensors properly and the actuator controls properly, so that whenever there is an issue, you ask the driver to take the control, and also driver has the responsibility to see if something going wrong. He should be taking control. Like for example, an ACC system or a brake system going from an internal braking function, he should be able to see that it's not going in the intended direction, and he should be ready to take the control. Okay, not initiated by the system, by driver itself. Then coming to one level up, driver should be monitoring all the time while system has full control as well. So system can control full longitudinal and lateral, but driver has to monitor and be ready to take over. And then the key will be robust detection of the scenarios. So how well you can understand the scenarios and be prepared with the system to meet this target. How well the system can cope up with the ODDs. And then with the driver who will be monitoring always and take over when there is an issue. Okay. Well, then comes the bit higher levels of automation, that is conditional high automation, which is driver is allowed to take off the eyes for a shorter duration, but should be ready to take over when indicated by the system. And system should be able to ensure longitudinal and lateral control in the given use cases, and should warn the driver to take the control whenever is needed. And then to have system fully controlling the situation and handling the situation while driver is eyes off, it should be a bit more on safety side to have proper redundant sensors. That means you cannot depend on only one sensor for a full autonomous operation. Remember Boeing 737 MAX situation, right? They have two sensors on both sides of the cockpit, but only one sensor was working, the other sensor was not at all working. There was no plausibility. So the defective one side sensor was used for taking a call whether the flight is going down or up, and MCAS system kicking in, where the driver was trying to pull the flight up, but the MCAS system pulling down, and vice versa. So the driver override was completely ignored by the system, right? So the plausibilization between different redundant sensors, all these things comes into picture. So we should ensure that both the sensing part is effective and the actuator control is also effective. so that you should have a redundant path to activate, so that you don't have loss of actuators or unintended actuations while the system is in control. And then when system finds something and want driver should take. All of you, I hope all of you remember the Tesla case. Tesla just got out of legal suit because the system warned the driver and driver didn't took over the control, right? The bridge versus truck case. So the driver should be ready to take over. However, he's not supposed to monitor all the time like the other automation levels. Then comes the next level, where driver is not required at all for a defined use case, for a defined ODD, operational design domain. But it needs fully redundant system to ensure that all the aspects of the boundary were taken properly. Like for example, you take a parking system, when you say an autonomous parking system. So you need to consider all the different domains, all the different use cases. And then those use cases, once you claim that they are handled by my system properly, then all those use cases should be properly considered from SOTIF perspective, from safety perspective, and from the operational availability perspective and performance perspective as well. The performance KPIs, everything should be met, right? And then driver should be able to take the control when required. Again, eyes-off is permitted. Then the last one, fully autonomous control where driver is not at all required. Currently, even though anybody is claiming L4, L5, we are still going with the manual mode plus autonomous levels, so that once it gets maturity, we'll go to the next levels, so that we can directly eliminate the driver. At this point of time, it's important that driver is also there. So there are multiple modes of the autonomous systems and all coming into the picture. On top of all of them, you're talking about very high levels of automation systems and all. But what is basic? That's your active and passive safety systems, your airbags, your seat belts, your primary braking systems. They should work properly, right? So your airbag, seat belt, braking systems and steering systems, these also should cooperate with the autonomous systems. So when you look at the autonomous level, you should not look for one particular system, always should look from the complete vehicle perspective. Otherwise, this will not be properly integratable with the vehicle. Okay. Now coming to the challenges for the autonomous, the primary challenges that we will see is, one is maturity of the systems. Like when you see from the human eye, 576 megapixels is the general consideration of human eye. Can you have a camera of that megapixels in the vehicle? No. So what is available today and how we can integrate that? Similarly, in the braking side, if a person is driving the vehicle, even though the accident is inevitable, I can still take a call to take a side track where the accident impact could be lesser, and I can take a call there. But can you consider the same in the autonomous level? I mean, if you remember iRobot movie, a person who is very hates robots because the robot chooses to save him because he has the more probability of saving than a little girl drowning. And since he is a soldier, he would always opt to save that girl, right? So human decisions are more robust, more diverse, whereas how do you make a system to work in that way, right? Then coming to the challenging road environments. So how far you test the vehicle? Can you test 100%? Roughly around 6 lakh kilometers is the road network in India. Roughly around 8 lakhs or 9 lakhs kilometers is the road network in US. We are the second or third biggest road network in India. Can you check for all kinds of roads? So how do we ensure that my system is autonomous, fully autonomous? So you too should take a considerable sample so that at least you can say that, for example, tunnels are some 1,000 kilometers. Then overall validation mileage you take, and out of that one, you consider a significant percentage analogous to the overall road network, right? So these aspects will be more challenging when you are pushing for the autonomous systems. Coming to the complex vehicle operations, like we don't handle the situation same, like for example, if you take a parking, we have different types of parking scenarios we face, right? We will be parking on a secluded place, we'll be parking on a road with only people walking there, we can park on sites where vehicles can go with full speeds. So how do we handle these situations? On top of it, it comes with the complex vehicle operations. Like you have more and more, as I think morning in the radar session somebody mentioned, right? These are becoming more and more complicated. Like you are having one thing which is running at 77 gigahertz, and now you have a microcontroller which reads the data. So how do you cope up with this data? And how do you handle this data? and fusing this data coming from radar and camera in the right time and reacting to that one in real time. How much time we'll have? 100 milliseconds, 150 milliseconds is more critical, could be anything, right? So understanding these things and analyzing them in a proper way will only help us to come up with a fully autonomous system. Coming to the complexity and lack of experiences and standards. As I said, the new standards coming up, 5083, 8800, these are bringing more and more challenges. And coming to the validation of the AD systems. So how do you verify? Because every driver is unique. So how do you replicate this driver's behavior in the validation of an autonomous system? How many driving licenses we have? How many patterns we have? So this requires huge data, right? And as of today, industry is starting to do that, but it takes time, right? Until then, how do you cope up with the customer requests? Because everybody wants L5 system as on today. So some of the challenges from the standards perspective: safety risk via 26262, security risk via 21434, SOTIF risk via 21448, and then safety and AI. At least we are okay with whatever requirement I write today to test it. Now imagine a requirement which is written by the system itself. Who should take the responsibility of testing? If you give the testing also to the AI, what is the guarantee that this AI, both the AI systems collude together and go with a quid pro quo situation? How do we guarantee that one? That's the biggest challenge, right? And this is still in the evaluation phase. How we don't know how it will evolve, and when it comes at the final level, it will be more challenging for the automotive engineers to cope up with that one. And then with the 5083, design and verification and validation of autonomous systems. As I said, the validation of AD systems itself becoming so complicated that a dedicated standard you will see in future, ISO 5083. Okay, so now when you want to launch a fully autonomous system, you need to consider all of them, and these 3 dots indicate the next coming 100 or 1000 standards. God knows how many, right? And sometimes we are thinking of merging SOTIF to safety, sometimes separate. So how they will go on. As of now, at least safety ones are not legally mandatory, but security becoming mandatory, and slowly more and more customers are getting aware and more demanding requests are coming. At least earlier, Indian market is not used to be that much demanding, but now we see more and more demanding Indian customers as well. So how do you handle the situation? Okay, and then coming to the evaluation of the systems, earlier we are dealing with fail-salient systems where detection is more important and stopping. Then came fail-safe systems as on today, where detection is important and moving to a safe state. When something wrong happens in the system, a sensor fails, a microcontroller fails, or an actuator fails, or the software fails, the importance is to the safe state. You identify a probable safe state, ensure that the safe state is achieved, and warn the driver. Now we are moving into an area with the AD to fail operational systems, where you have a failure, yes, you detect it, warn the driver, but you should be available for a certain duration after the failure. Now, how do you ensure that? That's where the essence of our discussion today comes in. So how do you ensure that when there is a failure in the primary system, the secondary system can still work? What could be the challenges to ensure that? What are the common factors that you handle? Okay. And when I say failures, faults, what kind of faults I'm talking about? I think in GHS, he gave a brief background on systematics and random hardware. I'll go in detail here. So systematics are more human-induced errors, what you and me do. I write a requirement, like detect the failure as soon as possible. Yeah. My lead reads it, says, yeah, fantastic requirement, go ahead. And then tester gets it, he says as soon as possible, he puts some 10 milliseconds or 100 milliseconds or 1000 milliseconds, whatever he wants, tests it. So how to check that it is correct? What time is correct? As soon as, immediately, sufficiently, ensuring. These kind of words are forbidden in requirement writing, right? Similarly, when you are considering the architecture, your design is not compliant with the safety goals. So architect makes the architecture, but not reviewed properly. So these all kinds of human errors should be avoided, right? And that cannot be avoided by any detection mechanism. That can be avoided only by ensuring that you have a proper development processes and all. Now, when it comes to random hardware, happens at the hardware level, and it is bound to happen. You can avoid a systematic failure completely, and you can never avoid a random fault. It may happen immediately after you purchase the system, or it may never happen. It's like a Chinese watch you buy outside. It may work indefinite time, or it will not work even the second instant, right? So considering these ones, now what kind of architecture I can consider, what kind of mechanisms I can consider to ensure that systematic and random hardware failures to be addressed by providing redundancy. Because when you are looking at a normal system, fail-safe system, it's okay to detect the system fault and indicate. But when you're talking about an AD system, I cannot afford these two failures, right? So I need to have a backup mechanism to come up and handle these situations, right? Now coming to this redundant architectures, what is redundancy? To have the same operation from a different means. And that different means can be an identical one and can be a diverse one. And what kind of redundant you can plan to design? One could be an active, that means both the systems are active at the same time, but one will be the in charge. The second one will be standby, but functioning fully. The second one, like passive redundancy, where second system will be completely passive, will not work, completely in standby, and then it will take over when the actual failure comes in. Okay? And then homogeneous and heterogeneous systems. So two or more redundant similar systems. The keyword is similar here. And you take both the systems developed same. Any examples? Like a sensor information coming to me in same way. Two sensors of same type I use and plausibilize them at a later stage. Now let's say heterogeneous, diverse implementation. Like I read one from the sensor, another from a numerical method. I read one sensor and one something altogether a different one to check. In commercial vehicles, if you are aware of J1939, you are aware for the speed, we can get two sources from brake system itself, EBC1, EBC5, EBC2, or because if it's coming from same source, we can have a dependent failure, then we will switch to one from HRV and one from this one, or one from CCO tachograph speed and the brake system speed, right? HRV or CCO or EBC1. So how do you consider that one? Two different sources, two different mechanisms, two different algorithms, two different devices, two different sources, anything, right? Taking one step ahead, what could be the differences? The primary thing is 2x development cost. You're talking about two independent implementations, which managements don't like, right? So cost can be lesser in the homogeneous side, and development cost will be more, but effective. So system and random faults mitigated because they're completely different, no common causes, no common mode effects, so it's more effective. Whereas homogeneous, you can handle the random faults, but the cost will be lesser, but in a more safety critical system, it's not a good idea to use it. Okay? Expanding that, so to achieve fail operational system, you need to have a proper redundancy to handle CCFs and CMFs, common causes and common modes, which you will see in the next slides, and with diversity. So your diverse design handles redundancy, mitigates the CCFs and CMFs, achieving a fail operational system. Okay? And from ISO 26262, a certain expert, that you should have measures for handling the dependent failures. As nowadays, it's not a challenge to implement the system. It's a challenge to prove that they are fail operational. Your power supply, your sensors, how can they be completely independent from each other? The whole industry is running around this redundancies only now for fail operational systems. Okay? Then, always remember high cost. So which one to choose among it depends on your design. If it's a highly complex SLD device, then obviously you need to take a call with the heterogeneous one. And if it's a less complex one like SLB or SLA, then I can live with two QM signals and plausibilizing to SLA, right? So it depends on your design, it depends on your project structures and the product that you are developing to do that one. I'll hand over to Mahesh to take over and explain about the different